This is a video on absolute value functions and their derivatives. So a little bit of background. The first piece of background is that um, the absolute value parent function is f of x equals the absolute value of x. All right, if you plug in a positive or negative x value, the positive value will always be your output. So the first big idea is that every absolute value function can be written as a piecewise function. So how does that look? Switch up here, written as a piecewise. Now, this means that I can take my original absolute value function and rewrite it with two parts. First, if x is greater than or equal to 0, so that means if I plug in a positive value, like if I plug in 1, just that positive value comes out. Whenever x is less than 0, like if I plug in a negative value, the opposite of that value comes out of the function. So if I plug in -5, the opposite of -5 comes out. So we can break up our absolute value function into a piecewise function. All right. So like for example, if you wanted to evaluate now -3, so f of -3, we know up here we'd have f of -3 is the absolute value of -3. That would give us 3. But then down here we just defined our function a different way. F of -3, I see that -3 would be less than 0. So I'm going to take the opposite of -3 and get +3. So we're just rewriting our function a different way. We can do this with every absolute value function. So for example, let's rewrite y equals 9x minus 2, the absolute value of that, as a piecewise function. All right, so first thing we're going to do is we need to break up our function. All right, what I would recommend doing first is figuring out where the function breaks. To do that, you take the inside of the absolute value function, and actually I'm going to do it a different way than that. So first, I know that my first rule is going to be 9x minus 2. I just take whatever's inside. All right, and my second part is going to be the opposite of whatever that is. So negative quantity of 9x minus 2. All right, now to figure out where the function rule changes, you just take the inside of the absolute value and set it equal to 0. So 9x minus 2 equals 0. Add 2 to both sides and divide by 9. X is equal to 2 ninths. So whenever x is greater than or equal to 2 ninths, I'll use this rule. Whenever x is less than 2 ninths, I'm going to take the opposite of what's on the inside. All right, so I can take any piecewise function and rewrite it as an absolute value function. To find derivatives of absolute value functions, because we're talking about differentiability, you need to rewrite the absolute value function as a piecewise function first. So let's do an example. Find the derivative of each function, discuss the continuity and differentiability of each function. So for the first step, for absolute value functions, we're going to rewrite as piecewise. So to do that, let's just take y, and that equals, well, it's going to be 7x minus 2 and negative the quantity of 7x minus 2. All right, to find where the rule changes, just set the inside equal to 0. So I get x is greater than or equal to 2 over 7 and x is less than 2 over 7. So when I choose values less than 2/7, I'm going to use this rule. When I choose values greater than 2/7, I use this rule. All right, let's clean it up a little bit, and I'm going to have y equals 7x minus 2 when x is greater than or equal to 2/7, or negative 7x plus 2 when x is less than 2/7. All right, so now the first thing is we have to discuss the continuity. Now, a trick is that absolute value functions are continuous everywhere. You can just kind of memorize that if you want. But if you really want to check the continuity and know for sure, you can think back to the other lessons we've done, and you can check if the left-hand limit equals the right-hand limit. All right. So if we just do that real quick with these two rules, I'm just going to take the limit as x approaches 2/7 from the left. I'll use negative 7x plus 2. You plug it in. All right. So negative 7 times 2/7 is negative 2 plus 2. I get 0. And the limit as x approaches 2/7 from the right of 7x minus 2, I still get 0. All right, and then f of 2/7 is defined because I can just plug in 2/7. So yes, it's continuous. All right, yes, continuous. All right. Now, for being differentiable, first you got to look at your piecewise function and take the derivative. All right. So when I take the derivative of my piecewise function here, the derivative of 7x minus 2 is just 7. All right. The derivative of negative 7x plus 2 is negative 7. All right, and we can say when x is greater than or equal to 2/7, and when x is less than 2/7. All right, so the derivative means slope, and I can automatically see that the left-hand derivative is different from the right-hand derivative. So I know the function's not going to be differentiable at 2/7. Okay, everywhere else besides 2/7, it's differentiable, but where the rule changes, where the slope goes from 7 to negative 7, it's not differentiable. So I'm going to say not differentiable at x equals 2/7. All right, because this at that point the slope changes from positive 7 to negative 7. You could also look at left-hand and right-hand derivatives like we did before. You could actually write it out like this if you want to. The limit as x approaches 2/7 from the left of f prime of x, or of the derivative, is not equal to the limit as x approaches 2/7 from the right of f prime of x, or we're talking about y. In this case, you would put prime. All right, now, just based on what we know about absolute value functions, all right, absolute value functions are shaped like a V. All right. So this point where they change is called the corner. We've talked about that before. So for this absolute value function, we can also say we have a corner at x equals 2/7. All right. So this is just the background. This is how absolute value graphs look. All right. So in order to answer the question, what I would say here is the function is continuous everywhere, but not differentiable at 2/7. And there's going to be a corner there. So these are the two parts of my answer, and these are some of the background behind it. All right. I want you to pause the video right now and try letter B. All right. Go ahead, pause the video, try letter B. And I'm going to get started. All right. First step, rewrite. All right. All right, so I just took whenever the inside is the same, x is greater than or equal to 12/5, I set this equal to 0. And then I took the opposite of the inside for when x is less than 12/5. Clean it up a little bit. Y equals 5x minus 12 or negative 5x plus 12. That's when x is greater than or equal to 12/5 or x is less than 12/5. So for the continuity, you can check the limits. It's going to be continuous everywhere because all absolute value functions are continuous. Well, absolute value functions are continuous everywhere. I don't see we're not dividing by anything. There's no square roots. It's going to be continuous everywhere, and we could check the left hand and right hand limit even if you want to. For the continuity. So our left hand limit is the limit as x approaches 12/5 from the left of negative 5x plus 12. Plug it in. We're going to get 0. The limit as x approaches 12/5 from the right, negative 5x plus 12. You're still going to get 0. So yes, it's continuous for the left hand because the left hand and right hand limits are the same. All right, so continuous everywhere. All right. Now, for the differentiability, just check the left hand and right hand derivatives. All right, so y prime is going to equal 5 and then negative 5. So when x is greater than or equal to 12/5 and x is less than 12/5. So I see that the slope changes from 5 to negative 5 at 12/5. So at 12/5, the function is not differentiable, though there will be a corner here. At 12/5 equals x or x equals 12/5, the function is not differentiable. There's a corner. All right. Now, there's one more type of absolute value question that might show up on the AP exam. And you saw it a little bit with limits, but I want to review it one more time here. All right. So This is just a special case of absolute value functions. Graph each function, discuss the continuity and differentiability. All right, so the first thing is I'm still going to go ahead and um rewrite this as a piecewise function because it's an absolute value function. You can always take absolute value functions and write them as piecewise. So I'm going to say y equals, just take the positive version of this, so x plus 7 over x plus 7. All right. And then I'm going to take the negative version of that part of the absolute value, so negative quantity x plus 7 over x plus 7. All right. Now, still the same thing, just set the inside equal to 0 to find where the rule changes. So at -7, -7 plus 7 is going to give you 0. So whenever x is greater than or equal to -7, you'll use this rule. Whenever x is less than -7, you use the second rule. Now let's make some observations here. I see x plus 7 over x plus 7 is equal to 1. So if we clean this up a little bit, y is equal to 1 whenever x is greater than or equal to -7, and x plus 7 over x plus 7 cancels out, so -1 when x is less than -7. And you can kind of see that from the beginning. You have x plus 7 over x plus 7. You know that's going to be 1, but it's either going to be positive or negative because I got these absolute value symbols. All right, so now what I see is this is my function. All right, I'm going to graph it real quick because that's part of the directions right here. It says graph. So to graph this, all right, the rule changes at -7. So I'm going to go all the way back to -7. 1, 2, 3, 4, 5, 6, 7. All right. Now it's 1 whenever x is greater than or equal to -7. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So whenever x is greater than or equal to -7, just the rule is 1. Then it says -1 when x is less than -7. So I'm going to put an open circle on -1 and shade the opposite way. All right, so this is the graph. All right, now when I look at my graph, I can see that we have a jump discontinuity at -7. Our graph is discontinuous at -7 because the left-hand limit, or the right-hand limit differs from the left-hand limit. All right, the limit doesn't exist at -7. All right, so yeah, so I know it's discontinuous at x equals -7. There's a jump discontinuity because it jumps up. Now, we know that for a function to be differentiable at a point, it also has to be continuous at a point. So I know the function is also not differentiable here because it's discontinuous here. So because the function is discontinuous at x equals 7, it is not differentiable at x equals, or -7, sorry, -7. Add your negative signs on here. All right. So to run back through the steps, first you rewrite the function as piecewise. Let's add steps in. We rewrote it. Next, we simplified. After that, we graphed. And in this case, we analyzed the continuity, so it was discontinuous, and because the function was discontinuous at -7, it's not differentiable there. All right, so I want you to pause the video, try letter B. And then I'm going to start going over it. So y equals x minus 3 over x minus 3, or negative x minus 3 over x minus 3. The function rule changes at 3. All right, so now from here, I'll just simplify. So I'm going to have y equals 1 or -1. So x is greater than or equal to 3. X is less than 3. Now from here, just graph it real quick. The function rule changes at 3. All right, so whenever x is greater than or equal to 3, sorry, not that, ignore that little point. Whenever x is greater than or equal to 3, your output's 1. Ignore this, that's not, that was bad. All right, and then whenever x is less than 3, it's -1. All right, now I can look at the graph and I see that it's discontinuous. There's a jump discontinuity. All right, at x equals 3, and it's also not differentiable at x equals 3 because it's discontinuous. Because there's a discontinuity there. All right, this concludes the video on finding derivatives of absolute value functions and their differentiability.